Okay, let's look at the second part of the boundary layer problem. Now we have a new problem. The last discussion, we talked about a scenario where the bulk part of the fluid is stationary and the lower plate is set into motion. And in this problem, it's sort of the opposite. Now we have a plate which is semi-infinitely large. The plate is stationary. The semi-infinitely large means there is a starting point of the plate, which is starting from 0. And then the x direction is extended to infinite. And also the perpendicular to the page, the z direction is also infinite. For the fluid flow, it is also infinitely high along the y direction and also along the z direction. Of course, everywhere infinitely. So the flow is sort of everywhere. The plate is being stationary, but the flow has a velocity, incoming velocity v, capital V. This is a constant. So the bulk flow sort of hits the plate from the tangential direction. So it's everywhere with a large bulk flow. In this case, we will develop a boundary layer which increases with the x position. So the boundary layer thickness we call the delta x. It is a function of position because at x equal to 0 at the beginning of the plate, the boundary layer thickness is 0, but it develops. However, it doesn't develop forever. Because when you are very far away down the plate, you will start to develop turbulence. And in those scenarios, you can no longer define a boundary layer thickness, and the things become harder to study. However, when x is small or when we are at the initial region of the infinitely long plate, the flow is laminar, and now we are focused on the laminar region of the boundary layer. And then we would like to obtain the boundary layer thickness and the fluid velocity. So we want to find delta x. This is a steady state problem. So it's a steady state problem. So they don't change with time. So no quantities change with time. Then we want to find the delta x at the boundary layer thickness, which is the boundary layer thickness. The boundary layer thickness in this context is defined such that Vx at the boundary layer this x evaluated. Vx is the x direction of the velocity on the boundary layer. It is 99% of incoming velocity v. So in this scenario, everywhere in the bulk part, it has a constant velocity v. So it's uniform. But the velocity will decrease in the boundary layer until it decreases to 0 on the plate due to the non-slip boundary condition. So we can find a spot where the velocity on the boundary layer is 99% of the bulk part. So that's how delta is defined. And we also want to find fluid velocity profile. In this case, we expected two velocity component. One is Vx. Vx means the x component of the velocity. It will be a function of x and a function of y. The reason it's a function of x is because, as you can see, as the flow goes down the plate, the boundary layer differs from location to location. So the velocity wouldn't be a constant in x. So it's a function of x. And it's also a function of y because it's obvious you have a zero velocity non-slip and a transient to the bulk flow. So it's a function of x now. And then in this scenario, there will also be Vy. Vy is also a function of x and y. So we also have y component of the velocity. It's not just the z component of the velocity. You may wonder why this is the case. If you look at the boundary layer, you can see this boundary, the boundary of the boundary layer develops as x increases. So if you only have x component of the velocity, then within the boundary layer, you would only have flow moving to the right horizontally. There is no way you can develop a boundary layer which increases with space. So the only possibility is you also have a y component of the velocity so that the fluid not only go along the x direction, but also go along the y direction. And that's the y component helps to develop the boundary layer. So we would also want to find the Vx and the Vy. So this is the problem set up. And then now we have two variables. In the last problem, we only have Vx and we used the momentum balance. But now we have Vx and Vy. If we use momentum balance along the x direction, we only get one equation. That means we can potentially only solve for one of them. But how about the other one? I mean, Vx is one variable and Vy is another variable. We consider these as two variables. So that means we need a second equation. And here is where the mass balance comes in. So for this problem, we will need to develop mass balance and momentum balance simultaneously. And that will help us to solve the problem. In order to do that, we would need to develop or set up a volume, control volume. So let's set up a control volume. So the control volume will be the space that we are going to develop the conservation laws. And let me zoom in. Let's do this. So this is the boundary layer. This time, let's set up a control volume from x to x plus delta x. And then let the height of the control volume be from y equal to 0. So this is 1. This is x. From y equal to 0 to y equal to delta. So the height of the control volume spans the entire region of the boundary layer. As you can see, the height of the control volume changes with x. So if you move your control volume to the right, you will have a taller control volume. But if we just fix it at a 1x position, that's fine. Then we will just have 1 delta x, the height of the control volume. So we have a control volume size. We have delta x And this delta x means the height. And then W. The W is the width of the control volume, which is along the z direction. It doesn't really matter how large or how small the W is. It's just a parameter we will eventually cancel out. The reason the z direction, the width of the z direction doesn't matter is because the flow is not a function of z. So it is uniform in z. So that's why it doesn't really matter. You can just give it a W. Okay, so for the control volume, let's first develop the mass balance. Mass balance means whatever flows into the control volume should be the same amount of whatever flows out of the control volume. So the mass rate flow in should equal to the mass rate flow out. And let me draw the control volume in a 3D way. Let's draw them. The 3D of our control volume here is delta x. Well, the height is delta x. And the width is W. So we would expect, let's see, what do we expect? We expect here Vx. Vx is a function of x and y. And then it will, well, Vx from the left is the flow into the control volume. And on the right-hand side, we have Vx plus delta x. It's the flow out of the control volume. This is the x direction of the flow. And on the top of the flow, we know that there is a Vy. There's nothing at the front and the back of the control volume because it's no z component of the velocity. So let us declare Vz is 0. If we see 0. Now what happened to the lower surface? Because of the non-slip boundary condition, we expect Vx evaluated at y equal to 0 means right on the plate equal to the Vy right on the plate equal to 0. This is no slip boundary conditions. Just using BC boundary conditions. Okay, so you don't need to worry about the mass flow on the lower surface or the no mass flow. So the mass balance equation should read as the sum of all the mass rate into the flow minus the sum of mass flow rate out of the control volume should be 0. And mass flow rate is the same as the density of the fluid multiplied by volume flow rate. So it is the same as density multiplied by the volume flow rate into the control volume minus density multiplied by the volume flow rate out of the control volume equal to 0. Now let's collect all the terms. The term, the mass flow rate that going through the left-hand side, so from like at x, the left-hand side of the surface, it is given by this thing. So left, let me just write down this left surface, we would have a mass flow rate, which is you need to integrate from 0 to delta, because the Vx is a function of y. You cannot just use Vx multiplied by the area of the surface. That doesn't work out because it's a function of y. So you need to use rho density multiplied by volume flow rate. Volume flow rate is velocity multiplied by the surface area. Now we need to use velocity multiplied by the integration of the surface area. So this is the velocity as a function of x and y. Then you integrate over the surface. The surface has a constant width w, while all in another way that the velocity doesn't change in the w direction. It's just multiplied by the width. And then the height is dy. So w dy is the infinitesimal area element. And you use w multiplied by dy, you get a strip. And then multiplied by Vx, you get the volumetric flow rate around that small strip. So let me draw here. This is consider strip dy. And the w dy give you the area of this strip. And then you integrate it from 0 to delta. It will give you Q in. So this is m dot from the left. This is the inflow. Now let's look at the right surface. Right surface, we still need to do integration. So we have 0 to delta x. We still have density rho. Now the velocity becomes Vx plus delta x. And again, we multiply by the area element, w multiplied by dy. This is m dot at the right surface. On the right, cross the right surface. And this is an outflow. Now let's look at the top surface. Because we are saying delta x is very small, we will eventually send it go to 0. So for very small delta x, the length of the control volume, then we can approximate Vy as a constant over this small strip. So the top surface, then we would have rho Vy evaluated at y equals to delta x. Because here we are not looking at Vy at every position. We only look at the Vy on the top surface. So rho Vy and multiplied by the area on the top surface, which is W multiplied by delta x. So this is m dot out. This is the outflow. So let's write down the mass flow with the mass balance for all the three surfaces. We will get this equation. we are saying the sum of the inflow plus the sum of the my subtract the sum of the outflow would give you 0. Then we can clean up these equations. We can say that the rho and the W are constant, and then you can like just cross them out. And then you divide both sides by delta x. So what we are going to do is on the left hand side, so if you remove rho and the W and you divide by delta x, you will get Vy at y equal to delta x equals to minus 0 to delta x. We have delta Vx. Oh, actually, here I had a typo. It's not delta x, it's delta Vx. I also had it the type of here in the diagram. It should be delta Vx. So we have delta Vx divided by delta x equal. As we discussed earlier, if you send delta x go to 0, then delta Vx divided by delta x equals to partial Vx partial x. So this equation becomes minus 0 to the integrated from 0 to delta partial x partial x. Now in this expression, the partial derivative is within the integral. It's on the integrand. You cannot move like directly move the differential sign outside of the integration if you have the limit of integration being defined depend on delta x or depend on x. So what we are going to do is something, we are going to apply the Leibniz rule. You may recall it from calculus class. If not, I'm going to write it out for you. The Leibniz rule. It's not a law, it's a rule. Oh. So it is a relation that for differentiating an integral with limits that is related to the variable. So it looks like this, dx. If you are taking the total, maybe let's do the dt, so that we have t and x being different. So now you take derivative to an integral. The integral has upper and lower limits which depend on the variable t. And then now you have an integrand which is a function of x and t. You integrate over the x. So in this case, if you want to move the derivative into the integrand, you need to consider additional terms. So the first of all, you move it. You can do the partial derivative, partial f, partial t. Vx. And then you need to consider the contribution of the boundary. So now you need to plus the function f evaluated on the upper limit. Then you take the derivative of the upper limit. Then you do a similar thing, but subtract what happens on the lower limit. So you evaluate the function at the lower limit and multiply by the derivative to the lower limit. That is Leibniz rule. Now, if you apply the Leibniz rule to our Vy, that's what you will get. You will get Vy to delta y is equals to minus d dx 0 to delta x dx dy plus capital V by d delta x. But here we have used a result that we have used the result Bx evaluated at y equals to delta. It equals to capital V. This is the definition of the boundary layer. This is, you may say, well, it should be 99% of V. Oh, that's true. Here we are using an approximation. So the 99% is a numerical criteria people use because we needed to define like a criteria anyway. But in reality, when people talk about the boundary, they actually means at the boundary or beyond the boundary, then the fluid steps to have the same velocity as the bulk part of the velocity. So that's the main spirit of being a boundary on the boundary. That's why we have to use this relation. Okay, so now let's see what do we get. We get an expression for Vy on the top surface. This is from mass balance. So you may wonder, okay, what are we going to do with it? We have Vx, we have Vy. We solved it on the top, but it is expressed in terms of Vx and a delta. And we don't know what is Vx, what is delta x. And that's what we need to continue to use. What we call the momentum balance. And we will use this equation later, but right now you can put it in your notes so that we have a result coming from conservation of mass. Okay, we have done with mass. Let's do it with momentum balance. Momentum balance in x direction. So momentum is a vector, and when you talk about the momentum balance, similar to you talk about the force balance, it's direction specific. So here we are developing momentum balance in the x direction. And then when we talked about mass balance, there is no direction. This is because mass is a scalar, and you just count for all the masses everywhere. So there is no direction. But for momentum, we need to collect all the momentum along the x direction. If you recall what we did for the last time, the last boundary layer problem where you have a plate which suddenly moves, and we had the momentum, which means the accumulation or the rate change of the total momentum equals to the total force acting on the control volume. Here we are doing the same thing. So now the X momentum balance, it should read this way. Here you have rho Q. Now we know rho multiplied by Q is mass flow rate. You have a mass flow rate m dot. M multiplied by V is momentum. And then you take a time derivative of momentum because Vx is a constant in time, like then you only get a dot on. Oh, let me put it the other way. So P is mv, and what we need is P dot dp dt. dp dt is v dt mv. So it is, you use product rule, m dot v multiplied by mv dot. And since it's a steady state, v dot is 0. So we just wrote that Vx and Vy is a function of x and y. They are not a function of time. So V dot is 0, so we got m dot V. So that's why the rate change of momentum would have m dot multiplied by V. So here, Q, rho multiplied by Q, as we just figured out, this is the mass flow rate. So this gives you the total momentum, the rate change of momentum. Now we need to collect the terms. So the rate change of momentum into the control volume, subtract the rate change of momentum out of the control volume. It should equal to the total force applied onto the control volume. Now let's look at let me still draw the control volume so that it's easier for us to look at the terms. So we have delta x, we have height is with delta x, the width is equal to Vx plus delta x of Vy. Okay, let's see. Then we also have shear stress. Tau Yx. Tau Yx is here tau Yx is into 1 equal to x. Now, before we analyze everything, I'm just putting down all the volume flow rate and all the forces you may expect. Here, I'm going to claim that tau Yx evaluated at y equal to delta x. That means the shear stress on the top of the surface is 0. This is because on the boundary layer, right at the boundary, we expected the Vx dy is 0 at y equal to delta x on the boundary. This is because right at the boundary, the fluid starts to have the same velocity as the bulk part, and there is like no gradient, no velocity gradient. That's why no shear stress. Okay, that's the recipe we have. Then we need to figure out the term by term. And if you look at the momentum transport in and out of the flow, let me write in another way. So you have m dot vx in minus m dot vx out equal to delta fx. Here we see Vx in the subscript and Fx, the x in the subscript. It means we are collecting momentum balance in the x direction. And when you count for m dot is the mass flow rate. Then you need to count the mass flow across all the surfaces. If there is a surface that you have mass flow out of the surface, then you need to consider that piece of the flow contribution along the x direction, like the velocity being on the x direction. So we will figure out that later on. Let us go term by term. So let's look again at the left surface. So let's see what is m dot vx. So we just discussed that we need to do integration. The m dot is rho vx multiplied by w dy. This is m dot. Now we use this multiplied by vx. This is the left term, or the left surface. This equals to m dot vx at the left. This is in term. Now we look at the right surface. The m dot part is rho x plus delta vx multiplied by w dy. This is the area element. And then multiplied by the velocity on the right surface, which is vx plus delta x. So delta vx. So this is m dot vx on the right surface. This is an outer term with momentum transport out of the surface. Let's also look at the top surface. Top surface, the m dot is rho vy, y equals to delta x. Then multiplied by the area, which is w multiplied by delta x. And then this is the m dot. M dot multiplied by velocity, the velocity of the fluid on the top surface. You may wonder, should we use Vx or Vx plus delta Vx? So here, since it's on the top surface, so it would have the same, we would assume it had the same velocity as on the bulk part. So let's just use capital V. So this is the momentum leaving the control volume from the top surface. This is an out. Okay. Let's look at the total force. Total force. Fx. Well, since there is only one component, so this is zero. but the lower surface is non-zero. So it would give you a minus sign, minus the area multiplied by the force, by the stress. The area is W multiplied by delta X. And the shear stress is tau YX, evaluate at X. So this is evaluate at not X, this is Y equal to 0, Y equal to 0. Okay, now we can put it together. The total change of momentum equals to the total force acting on the control volume. So the momentum balance equation would be this term rho Bx W multiplied by Bx rho multiplied by Bx plus delta Bx by W and multiplied by Bx delta Bx. And the entire thing integrated over it's integrated over dy. And then you have a term which is due to the flow on the top. And then be equal to the total force. Okay, so what we are going to do the next is, well, I'm not going to do the full process, but I suggest you try on your own. So clean up this equation, taking the leading order divided by delta x, set the delta x to go to 0, use the Leibniz condition again, and also use the result from our mass balance, which is you need the equation for Vy. Just use everything you have, and then you will clean it up. After cleaning it up, you will get a relatively nice looking a short form of the equation, which is still a result of the x momentum balance. So it will give you minus y tau yx evaluated at y equal to 0. It's equals to b dx integration over 0 to delta x rho capital B minus Vx. So you will get this equation. This is from mass balance. This equation also known as the von. So for momentum balance, this is called the von Hamel. Hamel momentum balance equation. Now let's suppose if we have Newtonian flow. With Newtonian, So we need linear fluid, which would be the assumption something for these people. We have tau yx equals to mu multiplied by partial dx partial y. So you can write the von Karman momentum balance equation in an alternative way. This alternative way is also called the von Karman momentum balance equation. They're essentially the same. It's just whether we are using the relation for a Newtonian fluid or not. So this evaluated at y to 0. Okay, so now if you look at this equation, we have eliminated Vy, or basically this equation is only like you only have Vx as a primary variable. You still have delta x with the boundary layer thickness, which we don't know. We will handle that later. So for this equation alone, it is primary equation in Vx. So we are going to use this to solve for Vx. The rest of it is we will solve for Vx. So there is no, like, this equation, you have partial derivative and you have integration. And it's a like integral differential equation and with a known limit of integration. This is not something we can solve analytically directly from this equation. That's why we needed to use approximate strategy. Now let's approximate velocity profile. X. Let's assume the x takes this form. You have a coefficient a plus by plus cy squared plus b y cubed. So you assume it's a polynomial in y, and the highest order is a cube, and you have 4 coefficients to be determined. As you can see, Vx should be a function of x and y, and we only write it in terms of polynomial in y. That means the coefficient a, b, c, d, they can potentially be a function of x. Now you may wonder, why do we use a three orders of polynomial? Like, why do we not use y to the power of 4th or 5th or whatever? And the reason is, here we have 4 coefficients. We exactly have 4 boundary conditions to determine the 4 coefficients. So that we sort of use this approximate profile partially because we want to fit it with a polynomial, and we know how many boundary conditions we can have. So the number of boundary conditions will help us to determine the number of coefficients. So let's have these 4 boundary conditions. Boundary condition 1 is at y equal to 0, have Vx equal to 0. Well, you may wonder, why don't we say Vy also equal to 0? Well, this is an equation in Vx. We approximate a velocity profile for Vx. So all the boundaries should be related, boundary conditions should have something to do with Vx. And also, since it's a polynomial in y, and all of our boundary conditions should be expressed in terms of y equal to something. So this is BC1, and BC2, so y equal to delta x. Right on the boundary, we know that Vx equals capital V. Boundary condition 3 is something we just discussed, that right on the boundary, there's no shear stress. No shear stress means no shear rate. So partial Vx partial y equal to 0. So it means no shear stress. Then the fourth boundary condition is at y equal to 0, the second derivative of velocity with respect to y equal to 0 is the second derivative. And you may wonder why this is the case. What's the physical intuition behind that? You can see the second order derivative with respect to Vx give you 0. It means the first order derivative of shear stress 0. So this is because Newtonian fluid. So the shear stress is proportional to the first order derivative with respect to y. Then the derivative of the shear stress give you second order derivative of the velocity. That's why it's the shear stress is 0. That means we have symmetric shear stress with respect to the plate. Symmetric shear stress back to y equal to 0 plate. Let me ask, well, what does this mean and where it comes from? You can think of the plate or the fluid you may have. Right now, we only talk about the boundary layer on the top of the plate, but it's no harm that you assume there is a mirror, that you have fluid everywhere, and then you have the same boundary layer at the lower part of the plate. Then you have a symmetric scenario. So in this scenario, you would have symmetric shear stress. And that's why we have this condition. So this is the mirror image of the condition. If you use these four conditions to solve for A, B, C, D, and after solve it, you will get the velocity. You will solve the, try it on your own. It's not hard, you just need to be patient. You will solve for Vx divided by capital V is equals to 3 divided by 2 y divided by delta x minus 1/2 y divided by delta x to the power of third. Okay, that's it. This is the velocity profile. We solved it. Well, you may say, well, we still don't know what is delta x. And we can figure out the delta x. So the way we are going to figure out is we are going to substitute this equation into the von Neumann momentum balance equation. Now let's substitute this expression into the Neumann equation. Now let's see, why do we do this? Here, we approximate the velocity profile by assuming it's a cubic in y, or a polynomial function in y. And then we solve this totally by using the boundary condition. And you may feel like it's so strange. We use the conservation of mass and conservation of momentum. We derived so many equations, but now we are only assuming a profile. Like what are we going to deal with the momentum balance? That's where we use it. So we assume the profile of velocity, and we use boundary condition to solve it. And then if we plug this back into this von Neumann equation, now you can see we already have an expression for Vx as a function of y, although it contains delta, that's fine. Then you just plug in, then you will get an equation totally in delta x. That's how we solve for delta x. So substitute this into the von Neumann equation. It gives us, so try it on your own. It gives us an equation in delta x. Now this is a differential equation for the boundary layer thickness. Now we can solve for the boundary layer thickness by solving this differential equation. This is just a first order differential equation, and you know how to solve it. You can just separate the variables. It's a very standard differential equation. We need a boundary condition, so we have a boundary condition for delta x, which is at x equal to 0, with delta x equal to 0, because at the beginning of the plate, the boundary layer thickness is 0. Now we can solve for this. So it solves for delta x is 4.64 square root of mu x rho capital V. Clearly, it's a function of x, as we discussed at the very beginning. The boundary layer thickness in this problem does depend on x. Okay, now once we have delta x, we also know everything about the velocity profile. Then we get what we want. So it's important to know that it is function of x. It depends on how far away the flow is flowed down to the plate. Now let's define a Reynolds number. So you learn in fluid mechanics what is Reynolds number. The Reynolds number for an objective, like for a plate or for a pipe, you would have a characteristic length in the characteristic length for the object, and then you will have Reynolds number for that problem. And then in our, actually, let me write it more specific. This is important. We actually have what we call the local Reynolds number. That's important to specify. Local Reynolds number. It is defined as Reynolds number at location x. That's why we call it local. It is rho capital V x multiplied by mu. So now the x become the characteristic length. Yeah. So that means the far away you are down the plate. Let me draw this again. This is over there. This is your incoming flow. The far away you are down the plate, the higher the Reynolds number will be. That's why there's only a finite region of the plate you would have a laminar flow. And eventually, if you are too far away, you will see turbulence flow. This is because you get a very, very large Reynolds number. And here you get laminar flow. So that means the Reynolds number depends on where you are. And now you can rewrite the boundary layer thickness by using the local Reynolds number. So you can write the delta x but the boundary layer thickness divided by the local distance where you are evaluating your boundary layer thickness. It should give you this. And again, verify it on your own. Square root of Reynolds number. Since Reynolds number is a dimensionless number, you square root of the number, it still give you a dimensionless number, so that's fine. So this is the entire ratio is a dimensionless quantity. It tells you this ratio tells you how the thickness of the boundary layer scale with the distance along the boundary layer. So you can see the left-hand side is the boundary layer thickness versus the distance. So it tells you how this proportion changes with Reynolds. And for this problem, for this particular geometry, for this boundary layer problem, the transition to turbulence typically occurs when the local Reynolds number is larger than the power of to the power of 10 to the fifth. So for this problem, it's important that just for this problem. The different problems would have different Reynolds number transition region. Problem transition to turbulence typically occurs when the local Reynolds number started to be like larger than or roughly equal to 3 times 10 to the power of 6. And now we have covered the majority part, the main part of this lecture. Let's also mention something that's helpful to know, especially in engineer or in industrial scenario if you are going to go to industry after you graduate. So this related to like drag force and power. Well, before that, let's first do a quick note of similarity transformation. Let's do a similarity transformation. We will see this later in a later section in a later chapter or topic. But then let's just mention it. You don't need to worry about where it comes from or how it is derived. You just need to know there is something called a similarity transformation. In this transformation, we define a new variable we call the eta. We define it to be y multiplied by the square root of rho v divided by mu x. Let's do this. And if you use this, you can go back to the velocity profile. Now we have our velocity profile. Is expressed as all the normalized velocity profile. We normalize it because we want to have a non-dimensional number. This is because this is the meaning of this ratio is the velocity compared to the incoming velocity to compare to the bulk outer velocity. That's why we have this velocity ratio. It gives you 0.3233 eta minus 0.005 eta cube. It's totally in a dimensionless form. This basically we absorb both x and y. You have two variables as a function of x and y. We absorb both x and y into a single variable we call the eta. And in this case, now your velocity profile is described by a single parameter or variable eta. And then we can also get the transverse velocity at the edge of the boundary. That means we can also find the Vy at y equal to delta. We had an equation for Vy. It's from the mass balance. You just be patient, figure out the calculation. You will get an expression for the velocity that's leaving the top surface of the boundary layer. It's also a function of x. And if you express it in terms of the Reynolds number, that it is. This is in case you are curious about what happens to the velocity along the y direction. Now let's talk about the drag force and the power. So the idea is if you have a plate which is stationary and you have incoming flow, so because of the viscosity, if you don't do anything to the plate would move with the flow. For example, if you have a leaf that drops in the river, as the river flows, the leaf will move with the river. It because of the viscous drag. And if you want to keep the leaf in place without being dragged by the flow, you need to apply force to it. That's the drag force. So now in this case, the plate, if you want to keep the plate stationary and in the face of coming flow, there must be a force developed on the plate and you need to keep it. And then you also need to apply power because you need energy input to always keep the plate in place. Otherwise, it will leave anyway. So this is about the drag force and power. So we know that the force is stress multiplied by area. So now we have on the plate, we have shear stress of Yx. So if you integrate the shear stress over the entire plate, you will get the drag force. Now, if you think about, you have a flow everywhere, not just on the top of the plate. You have also symmetric, you have shear stress on both sides of the plate. Then the drag force on the plate would be twice because one from each side. You have twice. You integrate from 0 to W. Well, since it's constant in W, you don't necessarily need to integrate over W. It's a constant in W. That's just multiplied by the W, the area. And you also need integration over the L, 0L. Now you have how Y X evaluated at Y equal to 0 Vx. So this give you the shear stress. Well, it's the same as 2W 0L mu partial V x partial Y evaluated at the value equal to 0 dx. Now we already know our expression for velocity. It is this expression. And you can use it. And when you see delta x, the boundary layer thickness, you use this expression for boundary layer thickness. Then it is just expressed as a function of x and y. And then you can plug in. So you can verify it on your own. It gives you 1.293 square root of rho. Mu is viscosity, the L is the total length of the plate. If you have a finite length of the plate instead of infinite length. W is the width of the plate squared, and the V is the incoming velocity. Cube, everything is under square root. Now this is the force. And in terms of power, we know power is force multiplied by velocity. So here the velocity is the incoming velocity. So you get power equal to Fx multiplied by V, the incoming velocity. And you get 1.293 on the square root of rho mu L W squared and the V to the power of fifth. What's going to calculate it? Okay, that's all I would like to see. It's a pretty long lecture, and you can review on your own. And the thing to keep in mind is all the logistics and how we not the logistics, all the logic of being behind the derivations. So we use the conservation mass, conservation momentum. Conservation mass give us an expression for Vy. Conservation momentum give us a relation between Vx and the boundary layer thickness. And then we assume a form of a solution, a cubic form in Y for Vx. And then we can go back to the conservation momentum to solve for the boundary layer thickness. Before we stop, let me leave you a homework. It's copied in a paste because the statement is a little bit long. I think it's better not to write this with my non-ideal pen so that you don't misread the numbers. So the problem is you have a laminar flow of air over a flat smooth plate. And if you wanted to estimate heat and momentum transfer near the surface, you have to consider the boundary layer effect. So now the air, the incoming flow is at a constant velocity V, capital V. And the plate gives you length, width, and the density of the air is also given, and also dynamic viscosity. You can calculate the boundary layer thickness at any position. Here you're looking at a particular given position. And you can find the Reynolds number, you can find the shear stress, find the drag force, and find the total power. So this is the problem.